All right, so we are on to circular reasoning, section 3, solving area and circumference problems. The learning goals of this section were to use the area and circumference formulas to solve for a circle to solve problems. Also calculate the areas of composite figures. Okay. The warm-up, determine the area of each circle, use 3 and 1400ths for pi. So I started by setting up the formula for each of these, and if I'm writing all the steps in, it makes it so it is more concrete and it stays in my brain longer. Then I substitute all of the numbers in for the symbols and for the variables. Then I'm going to do the parts to solve it, and I can and should use a calculator to get 16 times that, and that first circle should have an area of 50 and 24 hundredths inches squared, adding that label in at the end. Okay. Number 2, we have 3 and 8/10 centimeters as the radius, so 3.8 squared times 3 and 14 hundredths. Then I have 3.8 times 3.8 and times 3.4 to get me my final area for this one of 45 and 3,416 10,000ths centimeters squared. And a partridge in a pear tree. Number 3, I would take 9 squared times 3.14, which is going to be equal to 81 times 3.14. And that gives me an area of 254 and 34 hundredths meters squared. Making sure I add that label at the end. All right, I want to make sure that I'm going through the steps here to ensure that it stays stuck in my brain. They tried to trick me on this one. Do you see it? Do you see it? I needed to make sure it was 6 squared for the radius, not the diameter. I've been tricked on it before. Then we would have 36 times 3 and 14 hundredths. Type it in, and I get an area of 113 and 4 hundredths feet squared. To add that label in, I want to pay attention to those details. And so for this beginning of this unit, it's about circles and area and using that to solve some problems. We have circles all over the place, and now we can start thinking about them. Start thinking of them when it comes to math and solving them for circumference and area problems. Getting started, a winning formula. All right, so suppose that the circumference of a circle is approximately 157 centimeters. Describe a strategy you can use to solve for the area of the circle. Okay, well, so if I think of it, I would start by thinking of the formula of circumference is equivalent to the diameter times pi. Okay. Then, so I would start by using the formula. Okay. 2, I would substitute what I do know. 157 centimeters is the circumference. I don't know the diameter, but I do know pi. So 2, substitute what I know. All right. Then, if this is the case, I could do a one-step equation. So I divide both sides by my approximation for pi, and then that would tell me what the diameter is. Okay. And so if I take 157 divided by 3.14, I get a diameter of 50. So then my third step would be to solve for the missing dimension. Now that I have the diameter, I know the radius is half of that. So find radius from diameter. And so the radius then would be 25. Okay. Now that I know that, I would use the area formula. And so we know the area of a circle is going to be radius squared times pi, which is going to be the same as 25 squared times 3.14. And then 25 times 25 times 3.14 gives me an area here of 196 and 25 hundredths centimeters squared, finding that correct label at the very end. And so that is how I know it. And so my description would be right here, and then my actual solving it would be on the left. And so I did more than I wanted to. I just needed to do this in theory, but I wanted to show how I would solve it then too. Notice that this person is saying, when in doubt, use the approximation of 3 and 14 hundredths for pi throughout this lesson. What they're saying is if they don't put that direction in, that is what you use for pi. All right, solve for the area of the circle. Use 3 and 14 hundredths for pi. Hot diggity dog. Already did this above. So in question one, and this happens from time to time, in question one, they wanted me to describe what I would do. So I described what I would do. And then in question two, they're saying, go and do it. Well, I already did it in question one. So that is the end of my getting started. La 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 la. But then you keep going over your work because that's what good students do, and you realize that something didn't make any sense whatsoever. This can't be 196 and 2500 centimeters squared because this is 25 times 25, which I put in, and it was 625 when I got that. And so I know my answer has to be bigger than that because just that part is bigger than that. So I had to times it by 300, 3 and 14 hundredths. I'm guessing I divided it. And so I see the right answer here, and my area should not be this. Come on. My area should be 1,962 and 5/10 centimeters squared. All right. We all make mistakes. Our goal is to try to catch them as we go. Our goal is to keep on working and not to just say, I'm done with the problem. So look for mistakes. Pay attention to that when something doesn't make sense with your work. And then go back and see what you might have done. So I might have just wrote that down wrong. I might have typed something in wrong, but I knew it didn't make sense. So I needed to come back and I needed to adjust that. All right, so on this page, we have a maximum area problem for activity 3.1. And it is telling me about a friend who gave you 120 feet of fencing. You decide to fence in a portion of the backyard for your dog. You want to maximize the amount of fenced land. Draw a diagram, label the dimensions, and compute the maximum fenced area. Assume the fence is freestanding and you are not using any existing structure. So it can't be like up against the house or something like that. All right. So if I'm thinking about this particular problem, first I'm thinking about circles. And so if I start with the circle, it is saying that my circumference of the circle would have to be 120 feet. And if that's the case, then I would do what I did on the previous problem, which is circumference is equal to diameter times pi. And then I would put in 120, and I would put in my approximation for pi. I would solve for the diameter. Then I would take 120, I would divide it by pi, or my approximation for pi. And then I would get I would get a diameter in this case of 38 and 22, about 38 and 22 hundredths feet. And it would not be squared because it is the diameter. Okay, so if my diameter then is equal to that, and it would be about 38 and 22 hundredths feet. Now I could figure out the area of this, and then the area of this, I would have half of that, and so it'd be r squared times pi. And then I would have, let's see here, 38.22 divided by 2 gives me a radius of about 19 and 11 hundredths feet. So I would have an area of 19.11 squared times 3.14. And I could even do a radius here, and that would be 19.11 feet. And then I would times it by 19 and 11 hundredths feet. And I would times it by my approximation for pi. And so I get an area of 1,146 and 70 hundredths feet squared. And that is about. Okay. Now I read this question. So it says maximum area problem. Draw a diagram, label the dimensions, and compute the maximum fenced area. Assume the fence is freestanding and you are not using any existing structure. So I got that amount of feet, but I was kind of wondering, because it doesn't really say that I have to use a circle. And so I was kind of wondering on this one, if I used a square on this guy, and then I had 120 feet of fencing, I would have that be, let's see here, 30, 60, 90, 120. And then if I found the area there, it would be base times height. So the area of this would be base times height, or this one would be 30 times 30, since it is a square. So it's 30 times 30, which is going to be 900 feet square. Okay, so the circle is larger than the square with the same amount of fencing, according to this, unless I've made a mistake. This is a tricky one. Activity 3.2, composite figure problems. In previous grades, you worked with composite figures made up of triangles and various quadrilaterals. Now that you know the area of a circle, you can calculate the area of more interesting composite figures. A semicircle is half of a circle. A figure is composed of a rectangle and two semicircles. Determine the area of the figure. Okay. Well, first I'm going to work on the semicircles. And what's interesting to me is there is two semicircles. They have the same diameter. Since this is a rectangle, then that means they both have the same diameter and they would have the same radius. So the area of a circle is going to be radius squared times pi. Then I'm going to think of this as, let's see here, it would be 3.25, because it's the radius instead of the diameter, squared times 3.14. And then I know that I can use my calculator to figure that out. So 3.25 times 3.25, and multiply that by 3.14. And then I get an area of 33.16625 centimeters squared for the circles, for the both semicircles, because a half of it would be one, the other half would be the other, so I can just have that. For the rectangle, I know that the area of a rectangle is going to be base times height. And so for this one, I know that the area is going to be 13 times 6.5 centimeters. And then when I type that in, 13 times 6.5 centimeters, I get 84.5 centimeters squared. And since these are parts of shapes and I'm adding them together, my last step would be to take the circles or the semicircles, which is 33.16625 centimeters squared, and add to it the rectangle, which is 84.5 centimeters squared. And when I add those together, I will get my answer of the composite shape. And so or composite figure would be 117.66625 centimeters squared. Okay. Next one's a tricky one because we talked about it in class, but that top part is a trapezoid. And some people were trying to decompose the trapezoid into a triangle, a square, and another triangle, which kind of works if it's an isosceles trapezoid. However, since we are talking about it, it's something that we have that we're going to go over as we go. For a trapezoid, if I was to double the trapezoid with the very same type of trapezoid is how I spell it, and I was to flip it around, I would put them together and I would make a parallelogram. Well, a parallelogram, that formula would be the base times the height. Well, the base is this part plus this part. So it'd be the 6 plus 16 part for the base, and that would be times 7. The problem is that that's two trapezoids and I only want one. So I would multiply that whole thing by 1/2. And so for a trapezoid, any trapezoid, it would be 1/2 of base 1 plus base 2 times the height. Okay? And so when I look at this problem right here, I would have 22, it would be 11 times 7. It should be 77 unless I've made a mistake. Okay? And it would be 77 feet squared. And that's for the trapezoid. Now we have this semicircle. For the semicircle, the area would be radius squared times pi. This is 6 feet for the diameter, so this would be 3 feet for the radius. And so we would have 9 times 3 and 14/100, which is going to give me an area of the circle, which would be 28.26 feet squared. But then I need to make sure I divide that by 2 because I have a semicircle, and this lady over here said that's half of a circle. And so this area for the semicircle would be 14 and 13/100 feet squared. And so 14 and 13/100 feet squared for that part, 77 feet squared for the trapezoid. And when I add those together, I get 91 and 13/100 feet squared when I add the parts together. And so that should be for the whole amount. Last but not least, another one we talked about in class for sure. A figure is composed of a triangle and 3 semicircles. Determine the area of the figure. So first, I see that the semicircles all have the same diameter, 20, 20, and 20. And so for the triangle, I know a triangle is 1/2 of the base times the height, because if I took a rectangle with a triangle in it and I cut it diagonally, I'd get 2 triangles. Okay, so a triangle, two triangles can form a parallelogram or a rectangle, so it'd be base times height, but it's half of that. All right, then for this triangle, it would be 20. It would be 20 times 17.3 times 1/2, and the same of that is dividing by 2. And so 20 times 17.3 divided by 2 gives me 173 inches squared. For the semicircles, the area of the circle would be r squared times pi. The radius of these is 10 because they gave me the diameter, so it'd be 10 squared times pi. And that would be 100 times 3.14, and that would be 314. But that is the full circle, so I divide that by 2 to get the semicircle. And then the semicircle would be 157 inches squared for the semicircle. So we have 157, 157, 157, and then 173. So I could times this by 3 because there's 3 semicircles. I get 471 inches squared. I would add the triangle to that. And then I would get 644 inches squared for the whole composite figure. Okay, so I have to find the area of each of the parts, and then because they're all shaded in, I have to add them all together, and that'll give me my total area for each of those. All right, activity 3.3, shaded region problems. You have worked with composite figures by adding on areas. Now let's think about subtracting areas. In the concentric circle shown, R represents the radius of the larger circle, and R represents the radius of the smaller circle. Suppose that R equals 8 centimeters and R 3 centimeters. Calculate the area of the shaded region. Notice that concentric circles are circles with a common center. The region bounded by the two concentric circles is called the annulus. All right. So what I need to do is I need to figure out the larger circle, then I need to figure out the smaller circle, and then I need to take the larger circle and subtract away the not shaded smaller circle. So start with the larger circle there. And the larger circle is going to have an area of 296 hundredths centimeters squared. And so this is the larger circle. Then we'll have the smaller circle. And then we have 28.26, or 28 and 26 hundredths centimeters squared. And then, like I said, what we would have to do then is we'd have to take the larger circle and subtract away the non-shaded smaller circle. Okay. Then that'll equal the part that is shaded in. And so I get 172 and 70 hundredths or 7/10 centimeters squared that would be shaded. Okay. Next one, number 2. A circle is inscribed in a square. Determine the area of the shaded region. When a circle is inscribed in a square, the diameter of the circle is equal to the side length of the square. So since the radius here is 15, if I was to go all the way across, the diameter would be 30, and they said this is a square, and so this is 30. And so first I would want to find out the square. And that could be the side length squared is equal to the area because both of the side lengths are equivalent to each other. So I could say 30 squared is going to equal the area of the square, which is 30 times 30, which would be 900 meters squared is the area of the square. Then I need to find out the area of the circle. And for the area of the circle, it would be r squared times pi, which in this case is going to be 15 squared times 3 and 14 hundredths, which in this case is going to be 225 times 3 and 14 hundredths, which is going to give me an area of 706 and 5/10 meters squared. And now, just like with the last problem, I take the whole amount, the square part, because that was what was shaded in. Then I take away the part that's not shaded in this case the circle. And then what I'm left with is just the shaded part here, which is going to be 193 and 5/10 meters squared is going to be my shaded portion of this figure. Okay, so when I have just shaded region problems, I have to find the whole part. I have to subtract away what's not shaded, and that is one way to get my result of what is only shaded. All right, so on this one right here, we're working on number 3, which has 2 small circles are drawn that touch each other, and both circles touch the large circle. Determine the area of the shaded region. Okay. The tricky part about this one to me is that we have the center right here, and if we were to go right through this, if the radius there is 8, the diameter there is 16, and that would be true of the other one as well. If this radius is 8, then the diameter is 16, and so for the large circle, I would have a diameter of 32 and then a radius of 16. And that's the hardest part to figure out. Okay, now if I'm solving this, what I would do first is I would start by getting a small circle. And so I know the area is the radius squared times pi. I can flip that around, pi times radius squared. Then that would be 8 squared times 3 and 14 hundredths. That would be 64 times 3 and 14 hundredths. My calculator is going to tell me, even though I know we figured out a couple of these already. And I get 296 hundredths inches squared. Now what I would do is, since there are 2 small circles, I'm going to times this by 2 to get both of the circles. So both circles would be let's see here, times 2, 401 and 92 inches squared. Next, since I figured out the radius of the large circle, I can use that to use my formula then to get 16 squared times 3 and 1400ths, the approximation for pi. I get 16 times 16, and then I multiply that by the approximation for pi, and I get an area of 803 and 84 hundredths inches squared. My last step then is I would take the large, so the large circle, 803 and 84 hundredths, and I would subtract the not shaded smaller circles, and I should be left with an answer of 401 and 92 hundredths inches squared, and that would be what was shaded left here, and that makes sense to me because this radius is half of the radius of the big circle. That means that the area of the big circle should be 4 times the area of one of the smaller circles. Okay, now I look down at the bottom. Oh, hot diggity dog, I did too much work. Jimmy and Matthew each said the area of the shaded region is about 402 square inches, which is what we got. Compare their strategies. All right, let's take a look. They both have a thumbs up, so they're both right. First, Jimmy and Matthew found the area of one circle. All right. Jimmy took pi times 8 squared, the radius squared, and then he got his answer. That's exactly what we did. Matthew took pi times 8 squared, but he kept it as the more exact just symbol or pi, so it's 64 pi. All right, so that's different than what we did. This is what we did. Area of 2 small circles, doubled that. Area of 2 small circles, doubled that, but kept it as just times pi, so we didn't put in the approximation of 3 and 14 hundredths. Next, they found the area of the larger circle, so they both found the same thing. Small circle, 2 small circles, the large circle. The only difference here that I'm seeing is that Jimmy is using the approximation of 3 and 14 hundredths for pi, and Matthew is just using the symbol for pi, and he's keeping that kind of the same. Then they subtracted the larger one from the 2 unshaded smaller ones to get their answer, and it's about that many inches squared. And then for Matthew, in the last part here, he subtracted the 2 smaller unshaded circles from the larger shaded circle to get that answer. And then it looks like from here to here, he finally he actually approximated pi to be 3 and 14 hundredths and multiplied this out. And then this means that the area of the shaded region is about 402 square inches. So they got the same answer. The same answer is correct. It looks like I did Jimmy's method right there to get it, but they went around the same way of getting it. They found the same areas in the same order, and Matthew did not write down pi, or he did not use the approximation for pi until the very end. All right, so that should probably help us with what is on the next page. Okay, so now they're going to ask us questions about that. What did Jimmy and Matthew do the same? They both found the area of the smaller circles. Then the area of the larger circle. And last, both found the difference. Okay. What was different about their strategies? Jimmy used an approximation for pi 3 1400ths. Matthew used the symbol SYMBOL until the very end. Okay. Which strategy do you prefer? For you, it could be anything. I preferred Jimmy's strategy. And it doesn't say I had to pick why, but if I was to say why, because when I solved it without looking at the next thing down, I ended up using Jimmy's strategy. Okay. Determine the area of each shaded region. One medium circle and one small circle touch each other, and each circle touches the large circle. So this would be similar to the last question. So I'm always trying to make connections, and this one's kind of similar to that. If I look, I can make a diameter that goes all the way through both of those center points, and it touches the other side. And so since that is the case, this diameter would be 6, and this diameter would be 24. So the largest circle would have a diameter of 30, and therefore a radius of 15. And so for the very largest circle, I would want to have r squared times pi, and then I would have 15 squared times 3 1400ths. Then I would have 15 to the second power times 3 1400ths. And that is going to give me an area for the very largest circle of 706 5/10 meters squared. Now I need to find the two unshaded. And so for the one, it would be a radius of 3. And that gives me an area of the smallest unshaded circle of 28 2600ths meters squared. Then I need to do the larger unshaded circle, so that's going to be r squared times pi, and then that is going to be a radius of 12 squared times 3 1400ths, or 144 times 3 1400ths, or if I figure that out, 144 times 3 1400ths, which gives me an area of 452 1600ths meters squared. All right, and so now I can either add these two unshaded up and subtract it from this, or I can take the largest one and subtract the first thing and then subtract the second thing. Either way, I'll get my right answer. And so on the left-hand side here, I'm going to have 706 5/10 meters, and then I'll subtract. Actually, since it's in my calculator already, hard to see, I have the medium one, so I'll add to it the smallest. And so I'm going to subtract the 480.42 from my largest one. And that gives me a total shaded region of of 226 and 8/100 meters squared. Okay. Next one. Over here, it tells me a rectangle is inscribed in a circle when all the vertices of the rectangle touch the circumference of the circle. So this touches, this touches, this touches, and this touches. And with that, they showed the diagonal here, and they showed that that's 10 centimeters. And since they both touch the outside, that means that 10 centimeters is the diameter. And so for the circle, if the diameter is 10, then the radius would be 5. And now we can find the area of the circle. What I'm noticing is we're doing a lot of things over and over again, which is good for us because we should notice the pattern that is developing here. 5, 14/100, and that is 78 and 5/10 centimeters squared. Now I got to find the area of the rectangle. And rectangle is going to be base times height. In this case, it's going to be 8 times 6. In this case, it's going to be 48 centimeters squared. And now I take the bigger shaded portion. So I take the circle of 78 and 5/10 centimeters squared, and I subtract the rectangle that's not shaded. I subtract out what's not shaded of there, and then I should get my answer of 30 and 5/10 centimeters squared. And so that is the part that is shaded. So I calculate the area of the larger thing that would be all the way shaded in, then I calculate the area or areas of the smaller things, and I subtract the smaller things from the bigger thing. Last but not least, another tricky one, but I did answer a lot of questions on this one, and that's a good thing. So a circle is inside a regular hexagon. And the word regular is something you've gone over in the past. I know because I used to teach 5th grade as well. And so regular hexagon means even though it doesn't quite look like it, all of the sides are supposed to be the same length. So this says 6 inches for this one. They're all 6 inches. And so if I was to make this hexagon just into triangles, there would be 6 congruent triangles that make up this hexagon. And then, because that's the case, a triangle, we should know, we should know is area is 1/2 of base times height. And so for this one, it would be 1/2 times the base of 6 times the height of 3.2. And I could just take 6 times 3.2, and I know that if I divide by 2, that is often the same as multiplying by 1/2, and so I have an area of 9 and 6/10 inches squared for one triangle, but it's a hexagon, so there are 6 triangles. I multiply that by 6, and so all triangles or the hexagon is going to be 9.6 times 6. And so that would be an area of 57 and 6/10 inches squared for the whole hexagon. Now, just like with all the other problems, I have to figure out the circle. I have to figure out what's unshaded. And so they give me the radius for that one. And the radius is going to be 2. So I'm going to square the radius and times it by my approximation for pi. And I get an area of 12 and 56/100 inches squared. And so last but not least, I take what was all shaded, so my hexagon, first at 57 and 6/10 inches squared. I subtract what's not shaded, which is that circle on the inside. And that is 12 and 56 inches squared. And then what I'm left with is just what is shaded. So 57.6 minus 12 and 56 hundredths. And that gives me a shaded region of 45 and 4 hundredths inches squared. And that is the end of the examples of those types of problems. All right, so I made a mistake and I'm not going to erase it. I totally have the power to erase it, but I'm not going to. Here's how I do these. I do these first without looking at anything, and I try to solve them while showing my work. Okay. Then I think through them and I see if everything seems to make sense. And then from time to time, I will check the answer key. This one I was not so sure about, and so I checked the answer key and I was wrong. And I was thinking about it, and I was thinking about it, and I was thinking about it, and maybe some of you caught me. And the reason why I was wrong is I misread the diagram. When it says 3.2 inches, they're talking about just that section right there. And so that means the height of the triangle is not 3.2 inches like I have there, but it would be 5.2 inches going all the way up to there. And so I need to adjust this calculation just a little bit. It would still be how I solved it. The only thing that changes here is going to be 1/2 of 6 times 5.2 instead of 3.2. When I calculate that out, I get 15.6 inches squared. And there are 6 of those triangles, so I multiply it by 6 still. And I get an area of the whole hexagon of 93 and 6/10 inches squared. Then the subtracting is going to be different, obviously. So then I would take my hexagon, I subtract the circle, and I get an area about 81 and 4 hundredths inches squared. And so that should be my corrected thing. So as you're watching these, you're looking for me to mess up. You're looking to see if everything I'm doing makes sense, because maybe you're going to catch something that I don't catch. So I made a little bit of a mistake there, but I understand the mistake I made. And now next time through, I'm going to try to look at those diagrams a little bit more carefully. All right, so talk the talk. Here we go. Rupert's leash. Jamal loves his dog Rupert. On sunny days, Jamal keeps Rupert on a 12-foot leash in the backyard. The leash is secured to a stake in the ground. Okay, so we've got a stake in the ground. We have a 12-foot leash. Okay, so if that's the case, Rupert could go anywhere around here, all points that are 12 feet away from the stake. Let's say 12 feet. And so that would form a circle according to the definition of a circle. All right, so if the radius, because then they've given us the radius of 12 feet, the diameter would be double that at 24 feet. The circumference, if he went around in a circle, how far would he go? Well, circumference is diameter times pi. In this case, it would be 24 times the approximation they told us to use at the beginning, or the circumference here would be 24 times 3 and 14 hundredths, which is going to be 75 and 36 hundredths feet. So if he went all the way around in a circle, young Rupert would go that far. Okay, so it's here diameter, circumference, and area. All right, so area is going to be radius squared times pi. I could flip that around with commutative property multiplication, but then that would be 12 squared times the approximation for pi, which would be 144 times 3 and 14 hundredths. And if we type that in, 144 times 3 and 14 hundredths is an area of 452 and 16 hundredths feet squared is all of the stuff that he could conquer. All right. And I think that's all. Determine the diameter, boom, circumference, boom, and area of Rupert's play area. Use 3 and 14 hundredths for pi. Okay. Now, suppose Jamal wants to give Rupert a little more room to play. He uses a 15-foot leash instead of the 12-foot leash. All right, so we have the stake in the ground. We have a 15-foot leash instead of the 12. Okay, what is the area of Rupert's play area now? Notice it doesn't ask for any of the other stuff. It's just asking for the area of his play area. All right, so area is radius squared times pi, or 15 squared times the approximation for pi, which is 3 and 14 hundredths. 15 times 15 equals 225 times 14 hundredths, which gives me an area, or Rupert an area, of 706 and 5/10 feet squared. And holy cow, I know it's not asking for it, but you see how crazy this is? This one was 3 more feet. And it was 3 more feet, but look at the difference here. We have 706 minus 452.16. Holy cow. And you get 254.34 square feet of area. All right. So that's a lot more area for young Rupert by just adding 3 feet. So area is affected a lot, 4 times as much by addition in the radius. All right, cool. La 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 la, 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 la la la.